So singularities can exist. So warping the space-time fabric enough to be able to like teleport is possible. If you
Welcome, Garrett, to the World XP podcast. It's a pleasure to have you on. I think Garrett is a Renaissance man or something like that, because in his text to me, he said he can talk for days about religion, politics, real estate, businesses, health and fitness, freediving, spearfishing, and parallel universes, which obviously for the purposes of this conversation is the most important thing. But welcome, it's good to have you.
Yeah, man, I appreciate it. I've said it before. This is awesome, and I'm excited to talk to you about it. I think it's cool what you're doing, so let's get into it.
Yeah, man. So, of course, it wouldn't be right if we didn't drive straight into parallel universes for all the nutcases out there, including myself. But before we really jump into it, give sort of I feel like when people who aren't in the field of quantum physics, when they hear quantum physics, quantum mechanics, all that, like particle accelerators, all that sort of stuff, lots of ideas pop into their heads. So real quick, so everyone has the context of what it actually is, give us sort of a background on kind of what it is, how it works for dummies, essentially.
Yeah, so it's been a while since I've had to do that. So as short as I can, physics, obviously, I mean, just assume people don't know anything about this sort of thing. So we'll start from scratch. Physics describes how the physical world works. So if you want to know how quickly a ball is going to fall to the ground, you had to build a mathematical model to describe that. And then you keep going past that, like why does the apple fall off the tree? Newton came up with the theory of gravity. Physics is mathematical models that fits to describe phenomenon that we see in the real world. And that was, I mean, you say pretty simple, but it took forever for us to actually get accurate models. But it's pretty simple when you're talking about kinematics and balls, cannons flying, and things like that. Actually, one quick sidebar story. So this is I still can't believe this, but like in the medieval world, before we learned about gravity and stuff, or had a good accurate model of gravity, there's actually like old physical records of how they thought cannonballs would fly, and they thought that they would like, because they're basing it on their observations from like where they're standing, or not a cannonball necessarily, but like a projectile, like a trebuchet. And they actually have drawings like how they thought it would work, and it's like they imagined that it flew in like a straight line and all of a sudden just dropped straight down. And it's like how they actually believed it would work. It's just crazy to me how stupid we were. But anyways, so this stuff is pretty easy to understand for the most part. You could teach it to kids in high school and they understand all this stuff. But where it gets really hard is when you start talking about electrons and photons and things like that. So particle-like behavior. And we started to get some weird observations where the traditional, or what they call classical physics or classical mechanics, didn't really work. And it wasn't describing the behavior that they were seeing. And so in like the 1940s is when they came up with, I think, so my history and my numbers might be a little off there, but around that time is when they came up with the quantum theory. And the idea is that it started off with light behaves in discrete quanta. So a certain amount of energies that you can measure, like the smallest amount is quantized, and it's not continuous anymore. So you can't just keep breaking down the smaller and smaller pieces. It's just like us, you say, as a kid, you're always fascinated, like, what's the smallest thing in the world? You'd say atoms. Okay, but then smaller than that, you got protons and neutrons, and smaller than that, you get quarks. And we're always fascinated with that, like how small can you break things down? And you're always curious. So the next question is, well, how far down does that rabbit hole go? And well, the answer is it does stop. It doesn't go indefinitely. And as far as like photons are concerned in energy, there's a finite amount, and that's called quanta. And that's where the whole word came from. But at that level, quantum mechanics is a mathematical model that describes the behavior of those things at that level. And it's just really weird behavior. It's not like stuff you'd think. I mean, that cannonball actually does go straight down. Like it's weird stuff. And there's tons of weird examples of different phenomenon. And, people are excited about like quantum entanglement and teleportation and things like that. And that's where that sort of stuff can happen, is down in the quantum realm. And people want to always try and apply some sort of macroscopic like vision of that. Like Einstein even had a problem with this. He was walking with a good friend of his, it wasn't Bohr. Pally. And so he's walking with this guy. This is a scientist, and they were walking down the street, and the moon was out, and Einstein pointed at the moon and said, like, do you really believe that the moon only exists when you look at it? Because this is this weird thing in quantum mechanics. I can describe it in a second. And it's even Einstein had a misconception about how quantum mechanics really worked. That behavior is only evident down at the smaller level, and once things become macroscopic, that behavior doesn't exist anymore. It goes away, and it's because it just gets, things can only behave that way in very special circumstances. And so even as a kid, like to tell you, you can bang your head up against, quantum mechanics was like a way to silly way to describe, like, they'd say you could bang your head up against a wall 1,000,000 times and it's never going to go through. But if you do it 1,000,000,000 times, statistically, your head's going to go through it. And it's just not really true. I mean, it's fun to say things like that, but it's just not true. Weirder things happen, and that's the cool stuff, but it happens down at like a very small level. So, yeah.
It's chew on.
Yeah, I don't know if that does that answer what is quantum mechanics?
For me, it answers the question.
Okay.
We won't know if it answers it for anybody else until we have
everyone. Yeah,
but that's all right.
We'll focus on you.
So you mentioned one thing that I thought was interesting. It was a misconception about like the microscopic level, and I mentioned this to you earlier, and I know you haven't seen the show, but in Flash, when he basically goes so fast that he can go back in time and create like a parallel universe, he becomes very small. So where does that misconception come from, and how does it jive with, because you described it as the behavior of particles gets different as it gets down to that super small level, and I think a similar thing happened in Ant-Man. So they get down into like that weird sort of realm. So how does that? So like it's a misconception, but also when it comes down to the behavior at that size, where's sort of the disconnect there?
Well, I'd never heard about like that explanation with the is it Ant-Man or Flash or whatever it is, but I mean, it's pretty tricky. It's clever to say, well, it gets so small that things do behave oddly, and you can travel back in time and stuff like that. I mean, they're mixing a lot of things there, but I mean, it's clever, and it's kind of hard to like refute stuff like that.
So maybe let me rephrase then. What is the misconception that you were talking about for the microscopic, like the way that works?
Yeah, so it's just that. So there's a couple things going on. There's wave particle duality, which is wave particle duality is like this. This is the thing where people say like things behave one way. Most people have heard this. I feel like maybe not though, but when things behave one way when you look at them. So this is an experiment, the dual slit experiment, and you got a wall with like two slits in it, two holes where particles can escape. And you're shooting like a beam of like photons or electrons, it doesn't matter, but some sort of particle, could even be atoms, at this wall with these two slits. And if you just look at the screen on the back end where they're actually hitting once they pass through the wall, it'll have a statistical distribution that looks like waves interfering with one another. And it's really strange because even if you just fired like one photon at a time, this shouldn't happen. Photons can't interfere with each other in like different points in time, so that wouldn't make sense. So you have to describe them as waves that are coming out. They're just small packets of waves, not actual particles. But then so someone said, okay, that's fine, but what if I looked at the slit and watched which slit one of the photons went through? Once you do that, yeah, you'll see the photon at one specific slit or the other, not at both at the same time. But what you'll do is you'll affect what you see on the other end. It's no longer a statistical spread of waves. It's either one blop or the other, and that's it. So once they look for the photon, they disrupt the wave function. I'm gonna get crazy with you, but they break down this quantum behavior, and it now behaves classically like a photon. And so it's this observation that kind of screws things up and transitions something from like this quantum realm to this classical realm. And it's a weird thing that people still struggle with. It doesn't make a whole lot of sense. Why does the act of observing it affect this behavior? And we still don't have a good answer for that. This is, I mean, and a very attractive thing about quantum mechanics is you're dealing with stuff that we still don't even really can't make sense of. And we can say what happens. I can say that if you look at it, you're going to see two blops. And if you don't look at it, you're going to see a spread. But you can't say why that happens. And that's just a weird transition. And so it's hard for people, even Einstein, to make sense of, okay, well, how does this relate to something macroscopic, like looking at the moon? Is it the moon without looking at it, or is it only the moon when I look at it? It's hard to translate, and that's where people get screwed up. And even the best physicists out there, I mean, like Richard Feynman says things like, his famous quote is, Richard Feynman is one of the most famous American physicists of all time, and he's also a total badass. He is quoted as saying, if someone claims to understand quantum mechanics, then it's something about like they're the dumbest person on quantum mechanics in the room or something like that. You know, they obviously don't know anything about quantum mechanics. So the more you think you know about it, the less you actually do. Is kind of a quip that he had, but obviously it's only true in certain contexts. But
yeah, I mean, it makes sense though, because if the more you understand, the less you understand, really, I guess, if that makes sense.
It screws you up.
Yeah, that's wild. All right,
it's weird.
You mentioned 2 points in time. Let's do it. Parallel universes. What's going on? Do they exist? Is there another version of both of us somewhere?
The fun thing is you can't. The reason why it's so fun and people like it is because we can't prove it wrong. I can't disprove that there's parallel universes. So it's possible, and I can't say that it does or doesn't until we have some sort of apparatus that can travel between them and create wormholes and things like that. But until we can do that and rip the space and time fabric, I mean, it's not going to happen. You can't test it. But I think that this is probably the most interesting thing in like the science world, like where the debate lies. And so I'll try to build it up, because most people just hear parallel universes and think it's cool, but where does it come from? And it's even a little bit more interesting. So I had this like discovery as I was like going through like trying to understand quantum mechanics. And what clicked with me was how quantum mechanics gets rid of deterministic outcomes. So, and this gets into like a little bit of like religion. We won't go down this path, but you'll see the connection here in a second. So the phrase "everything happens for a reason," or everything that happens is meant to be, is kind of like an interesting thing that people say, and I always kind of question that, like, is that true? Is everything determined? Do we have free will? Things like that. Right. And quantum mechanics kind of proves that nothing is deterministic, that the free will could very well exist, and we aren't just robots carrying out a script, which is cool. So it gives everyone the freedom back. You're now an autonomous being that can make your own decisions, and everybody wants to feel that way.
I do want to
Sam Harris think later. What do you know what Sam Harris is? Yeah, and his arguments on free will. That's pretty wild. Yeah, I'm still trying to wrap my head around it, to be honest. But so in the physical realm, things behave statistically and not deterministically. And so once I came to this when I was like doing some modeling for like missile defense stuff, and we had a random number generator to create like random trajectories. And I had a late night Friday debate kind of like this at the office, trying to understand like what truly random meant. Flipping a coin, is that really random? If I can give you the physics of a coin flip and I can replicate it every time, that it's no longer random, right? So there's actually, it's pretty deterministic. And so you can kind of predict what the outcome, like if I had a robot that was watching you flip this coin, as soon as you left your thumb, if this robot was smart enough, it could predict whether it's going to be heads or tails. So it's not probabilistic. It's not purely random is the right way to say that. Down at the core, things, instead of having a question like, is everything deterministic? But once you get into quantum mechanics, you'll learn that down at the core, everything is statistical, and that nothing is deterministic. And so you're like, whew, like, okay, cool, got it. Can totally scratch that off. I mean, that was a mind-opening thing for me. But then I met Dr. Lev Vaidman. Dr. Lev Vaidman is the author of the Many Worlds interpretation of quantum mechanics. And this is this parallel universes stuff. And so I got to meet him and have a conversation with him. He's very quirky, very interesting guy. He's also a co-author on so I study weak values. We can talk about my research later if you want, but I study weak values. It's a quantum mechanical phenomenon that gives you some weird outcomes, and we're trying to use them to build better sensors. This guy was also one of the co-authors on the seminal paper on weak values. So it's just weird that he's also the author of the many worlds interpretation of quantum mechanics. So what's going on here is this. You have so everything you've known from like when you're born to now is just one single thread. But what the many worlds interpretation is saying is that every decision point, I mean, every decision point you make, not just like, do I brush my teeth now or later, but like every little thing, like the words I'm saying, how I move my head, all that stuff is a decision that you're making, whether it's unconsciously or consciously. Okay. Well, if that's true, okay, and you're making these decisions, well, first of all, everything seems, so let me try to make sure I'm laying this out right, because I don't want to screw anyone up and then have to come back. So what the many worlds, so first I'll lay out what the many worlds is. What the many worlds is saying is that as I'm going through and I'm making these decisions, there's also a parallel universe or another universe where I've made the other decision, and I've then got a tree of other decisions after that, right? So at a decision point, you can break into 2 or 3 or 4, whatever you'd like. It's a tree that keeps evolving into more and more trees. And that's what this many worlds thing is like in one world, in the world you live in, you have selected this tree, but a clone of you in a different universe selects the other path, and so on and so forth, and it becomes this big infinite tree. And what it does is it brings determinism back in. So Lev Vaidman is a diehard determinist. He says, no. So this is the fun thing. So physicists, at least for physicists, I'm going to just nerd out for 1 second. So physicists,
nerd out all you want, bro.
Dude, so I mean, this is cool, like standard talk, like many worlds, like, oh, multiple universes, that's crazy. You know, it's like, oh, there's in some world there's a version of me who's like, you know, Jeff Bezos, but this is even cooler than that. Well, maybe for someone like me. So leading up to the quantum revolution, you got to imagine the culture of physicists and stuff. So they're usually like, you know, back in the day, like the gentleman scientist who's like doing chemistry in his basement kind of thing and actually coming up with new discoveries and stuff. These people are very like arrogant, like Renaissance men, and it's, you know, they're also usually like wealthier because they can afford to do this stuff. And one of the, you know, in a scientist, you know, arrogance isn't going to escape them for long. So these people, you got to think about their mindset. They're learning more and more about the universe, especially like down to the smaller and smaller level. Like chemistry is starting to actually form with physics other than being alchemy and things like that. And so we're actually trying to make sense of the world. And the physicist's goal here is always going to be a cosmologist's goal. Cosmology is the study of the universe and the history of the universe and all this stuff. That's what Einstein was and all of them. So the goal is to get like a binding theory of everything. You know, the universal theory to describe everything. We've got these different theories, and like quantum mechanics isn't quite settled with classical mechanics. And so people are struggling with that. Like, how come you can't combine the two? It doesn't make, you know, you got to transition. So you have to make a decision when you're looking at something, whether to describe it classically or via quantum mechanics. And some things can be described by both. But not all things, and that's a big problem. So people want this universal grand unifying theory to describe everything. So if you've got some sort of behavior you want to describe, you pull out your books and you've got universal theory and you rock and roll and it's game over. You can describe anything. Well, it doesn't work like that. We're not that smart. We don't have a theory of everything. But leading up before quantum mechanics, we thought we were going to get there. And quantum mechanics really freaking threw a wrench in that. So everybody's thinking, you know, if I just have enough information about a system, I can tell you what's going to happen. What does that sound like? That's determinism. If I can tell you enough about that coin flip, I can tell you enough about how this thumb leaves it and all that, and where the coin is placed, I can tell you what the outcome is. That's determinism. What that proves, if you can prove determinism is real, that is, you can predict anything given any sort of set of initial conditions, and there's no random variable, then I can tell you the outcome of the rest of the, if I get a powerful enough computer, I can put in all of the variables. I can tell you the outcome of whatever election you'd like. I can tell you the outcome of what's going to happen to the U.S. with all this craziness going on right now. If you have a smarter computer and you put in all the variables, you should be able, in theory, to predict all of it. Okay, so hang on 1 second.
Got it.
That's what these determinists want, and that's what these physicists were hoping to get to be able to prove, like, this is something we can do.
All right.
Quantum mechanics comes in.
Sum this up for everyone listening, and then you can tell me where I've
yeah.
like, I'll say old, but physicists back in the day, they've got the classical theory of kind of like, they want to get to a classical physics theory of everything, how the world works.
Yeah.
And because they think that they can get to that, essentially that means that they would be able to predict everything given the initial conditions, initial variables. And so the quantum realm, I guess, messed that up because of the behavior in that realm does not jive with the classical physics world.
Yeah, and there seems to be randomness. So you can't, down at the fundamental level, you can't predict everything. Gotcha. Quantum mechanics is literally, so the scientists were chasing the universe. They wanted to be able to solve everything that could ever happen with the universe from start to finish. I can tell you what's going to happen if you give me this theory and you give me enough inputs, enough variables. Quantum mechanics was the universe's way of like, that's the universe's middle finger to the scientists that thought that they could figure out what the heck was going on. And that's got to be the coolest thing about all this. So back to many worlds. So quantum mechanics flicks off the scientists that think they can figure this stuff out. The hardcore determinists that want to that want the universe to be deterministic, not random and wild. They want order to the chaos. And quantum mechanics says, no, Lev Vaidman comes along and says, in fact, determinism is still compatible with quantum mechanics because you make your decision and the physics that we know, the determinism is in line with that path line, the line that you and I know.
Right.
And it's compatible with you making the other decision. That line is also separate. Determinism stays and the randomness goes away because you don't pick one, you pick all of them. Every single one of your options are chosen simultaneously, and they continue to do throughout the rest of that tree. So determinism is back in, determinism is back on, and quantum mechanics also still works. It's very strange. I think it's a cop-out. I think it's bullshit.
I was about to say that. I was like, that just seems like a way to have your cake and eat it too.
Yep. Yeah, it's bullshit. So I pressed Lev on this, and we were at a conference for weak values, and he's a Renaissance man. He's going to like he's going to do that, and he was like having a drink, and he played chess in the middle of it, and then he was going to go to some a violin concert or something later on. He's pretty wild dude, and he's a bit, you can sense his arrogance when you're talking to him, but like in a good way, and like a fun, quirky science way, right? I mean, any dude that famous for this stuff is gonna be. So I mean, no offense by that, but I asked about this, and I was like, doesn't that just seem like a cop out? And he didn't know what I meant by that. He's foreign, and so as a colloquialism, I guess, I was like, it just seems like you're cheating the system, you know? And then he like clicked, and he's like, no. And it was like he got fired up for sure, but in a good way. Like he was smiling the whole time, and he's like, no, it's real. Like this is what it is. He goes, this is how it works. And I said, but Lev, nobody can ever do an experiment to prove you wrong. And he's like, that's right. And like, so you're fully aware of like this is just like I say it's bullshit. I mean, it's possible, right? We can't prove it wrong, so I can't say that's not it. But yeah, it's he loves it. Like he's grinning because he's like, prove me wrong, you know, and they can't. And he's even got like an app. There's a many worlds interpretation app you can get on your phone. And he's like, you know, his quip was like, he goes, if you're trying to figure out whether to stay in or go out to the movies, he goes, you don't have to choose. He goes, you can do both. Just get on the app. And I'm like, oh my gosh, it's so dumb. It's not dumb. What's that?
Is it his app?
Yeah, I guess so. I heard his
what a racket.
Yeah. I don't know if I'm sure he's getting some kickback for it, but it's so dumb. It's not dumb. It's just, it's a hard one. It's a hard pill to swallow. I mean, he's welcome to it, and so is everyone else. So then you get into the fun stuff, and you're like, being able to pass between parallel universes, and that's where they come from, by the way. So like that's the basis of it, and then you get into the fun stuff of Ant-Man or Flash, you know, teleporting back to a parallel universe and coming back in time and all that stuff, and yeah, time travel is a weird one. That another thing that like hasn't been proven wrong, and that one is a little bit further and harder to explain. Like relativity is a fun thing, but it's definitely hard to wrap your head around.
Yeah. So parallel universes are possible then, is what I'm taking out of this
conversation. You can't prove it wrong. So here's an example of something you can prove wrong that is also quirky. So parallel universes, we can't prove that they don't exist.
Right.
If you can maybe I don't even know if we had like the equipment. I can't even think of an example where you have equipment to be able to do that. I mean, you could describe some sort of like storybook way to test it, right? But like, okay, I traveled to a parallel universe and there it is. And then, you walk it back. But I mean, I don't even know. It doesn't even seem real.
Wouldn't that mess up the parallel universe then if you traveled to it and then it hadn't accounted for that? Or would that just create another decision tree?
No, just more decision trees. Dude, I'm telling you, it's just like, here you go. Like, just throw more trees at it.
That would be wild if it actually worked that way.
Yeah. So all right. One thing.
All right, keep going.
So there's lots in science that like people want to be true so bad, but it's like I read popular science articles and stuff people send to me, and it's just like they blow up the dumbest shit. But it is actually really interesting down to like the level of the science that's going on. One really good example is teleportation.
Ooh, more fun stuff,
dude. So being able to like travel between like multiple universes and stuff, people say like you need like a wormhole, and you have to like really stretch space-time. Like I mean, the classical example is, let's see if I got a piece of paper here somewhere. Oh yeah, I've got sticky notes. Cool. The classical example is like what a wormhole is. So like this is, if we live on what they call, so in the physical world, they call this a flatland. It's just a 2D space, and we're these little creatures that live on here. If you wanted to like pass from one end of flatland, so I want to go from, let's say, I don't know if you can even see this stuff.
Yeah.
I want to go from here to, if I want to go from circle 1 to circle 2.
Right.
Okay. Well, one thing, I can't obviously just teleport from here to there, but what you can do is fold the paper over and then make sure they're on top of each other, and then you pass through just like that. And so you poke a hole into here. And so then that's the idea, is that is now my wormhole. So all I have to do is figure out how to create that wormhole between the two. And how you go about all that stuff is where it gets tricky. But it doesn't, so far, it doesn't seem impossible. And you just need enough energy and to know how to bend space-time enough to do that. I mean, if you look at like a graphic of like how space-time bends around masses, like a black hole, which is a singularity in the space-time fabric, because it essentially, like, space-time fabric bends towards masses, and if you get something that's massive enough, it's going to bend to a singularity where you've got this hole that could be ripped, and if it's bending space-time around it at that point, then in theory some weird stuff could happen, and you could end up somewhere else. I mean, that's kind of the idea without like explaining how they think that happens.
Okay, so real quick, just so we get some context around what you're saying.
Yeah.
So when you say the space-time fabric, like when most people think of a black hole, they just think of like something that's sucking in all the light that's in the universe somewhere. Mm-hmm. But you think of it in a different way. So when you say like singularity and space-time fabric, what, just like real quick definitions for like, what do you mean by those things for those listening? Because I think I have an idea of what you mean, but I'm not sure that other, like, the listeners might. Yeah. Especially if they're on Spotify and they didn't see your paper thing. So just some context.
So the easiest way to understand what's going on this stuff is to, believe it or not, to dumb it down and simplify it to scientists. And what this means to scientists is, let's go from 3 dimensions to 2 dimensions. And that's this flatland stuff. And so if you imagine, instead of 3-dimensional beings, which we are, and I can move in X, Y, and Z, imagine we're 2-dimensional beings and we can only move in X and Y. That's the easiest way to conceptualize what the heck is going on. If anyone starts to learn about like higher dimensions and stuff, that's what they'll do. You'll start off in flatland. You start off in line land, which is just one dimensional, and then you'll move to flatland, and then you can say, okay, now let's think about what that would mean in 3 dimensions and beyond. And high schoolers can think about this stuff pretty well, but it's got to be. So when you talk about like space-time fabric and bending fabric, we go back to flatland, to 2 dimensions, and you can think of like space. I'm talking about like actual space with the sun around it, and you always see the orbits, and they're all kind of like flat. Like you got the sun, and you got all these other things on the outside, on the perimeters, and they're rotating around, and they're in this flat plane. You think of that as like being on a trampoline, right? And the sun is in the center of the trampoline, and the trampoline is warped all the way down to the weight in the middle. You put a bowling ball in the middle of the trampoline, that is the sun. The trampoline bends in towards this bowling ball, and you can think of you're still being on flat land. You're still this human flat person, this 2-dimensional person on the surface of the trampoline. The trampoline to you is still flat and everything's fine. You don't see this bend. You don't see how the trampoline is bending because you live in 2 dimensions. The bend is in the 3rd dimension and doesn't make sense to you, but you can experience it. You're still going to get pulled in towards the center. So you can experience it, you can measure it. If you had flatland scientists, they can measure how much they're accelerating towards the center, but they wouldn't know why. And so we can, because we're 3-dimensional beings observing this, we can say, oh, you're bending space, the fabric of the space they live in. Forget time, the physical space, you're bending the fabric of that physical space, the fabric in this case being the surface of the trampoline. And so you extend that to 3 dimensions, and voila, you've arrived at the 3D space-time fabric that is being bent, in a sense, by these large masses and black holes. And if you put something, yes, go ahead.
So basically, I'm trying to visualize like a graph in my head.
Yeah.
So you've got X, Y, Z, and then instead of it just going straight into the trampoline, it just is pulling the 3rd dimension or bending the 3rd dimension with it, essentially.
Yeah. That's right.
Yeah, that makes sense. Okay.
Yeah, so,
got you.
That's right. Yeah, and so what a singularity is in this idea, you want to get to where you can, you think of the trampoline's pretty damn tough, okay, but you want to be able to like have the trampoline bending so much in like certain points. I mean, get to like a giant fucking trampoline, excuse me, a very big trampoline, and you've got different bowling balls in different areas and stuff, so not everything rolls into the center, and it's pretty rigid. Well, you need to be able to, if you want to like travel between 2 pieces and rip this fabric of this trampoline, you need a really, really heavy masses. I mean, you put a golf ball down there, you're going to see a small indent. You put a baseball, maybe a little bit more. Put a bowling ball, a lot more, so on and so forth. Once you get to like something that's really, really small and really, really massive, that thing is going to be locally bending really, really quickly and steeply. And if it bends so steep, that you can't measure the width of it, and the depth of it is infinite. That is what like a singularity would be called.
Gotcha.
So it's asymptotic without end. So it's infinitely deep and narrow, and that's what a singularity would be called. That's what black holes essentially are.
So it's not really sucking all the light in. It's just bending it's bending it in a way that we can no longer see it.
Yeah, so what's cool, the whole black hole thing, why it's black, is they got this what they call the event horizon, and so that's the width of it. We used to get a cool picture of one recently, right? It came out like 3 years ago or something like that. The picture of the black hole, you know what I'm talking about? It's pretty famous, yeah. And it's got that red ring around it, telltale red ring everyone loves, the ring of fire, and that's the firewall. And there's a lot of weird stuff. There's still a lot of debate too about what's going on there. But what isn't debated is that light isn't escaping within there. So if photons travel within the event horizon, they fall into anything beyond photons or whatever. If Eric Jennings got close enough, if you got past that event horizon, you're gone. Nothing escapes. So light doesn't escape. But that's of course why it turns dark. But on this horizon too, there's also this weird thing, and I don't know enough about it to explain, so I'm not even going to pretend to. But there's some weird debate going on amongst cosmologists. Cosmology, again, study of the universe and history of it, and all these weird, quirky theoretical physicist questions about like how information gets exchanged there. So like if you entangle a pair of photons and you send one of them in and past this firewall, and then you've got one, like what does your information say about that, and vice versa. So there's weird questions that you can play with around this firewall of black holes that we still don't quite know the answers to. And yeah, they're really freaking cool, and they also give people in shows, something to work with, like, okay, so singularities can exist, so warping the space-time fabric enough to be able to like teleport is possible. If you could create a local black hole in your pocket, like, and then also direct it to where you're able to do what you want to do with it. I mean, other than just getting ripped to shreds.
Would that be the concept though, essentially, is to create a singularity that you could kind of get through, like, or what, when we were talking about time, what were we talking about? Time? No, was it time travel? Yeah. So is that the concept, to create a singularity where you can just, like, when as you folded the paper, to just bend it enough that you could just hop through to the other side?
Yes, but in practicality, like at least in a black hole, and so in a black hole for sure, you're gonna get ripped to shreds. Like, you're not gonna survive. A human won't survive that.
No, of course.
But that's kind of the idea, is information can pass. Maybe you can be reassembled on the other side or something like that. But actually, which brings it to another cool thing. So that we can't actually. This is one of the things where you can prove that it doesn't exist, and that's what I was trying to say earlier. It's called the no clone theorem. So you can't actually teleport, so you can move yourself. I can move Eric Jennings as fast as I want anywhere else, and perhaps I can teleport you somewhere via black hole, and as long as you survived it somehow. We made some special capsule that made you impervious to the gravitational stretching and lensing, so you somehow survived your transport to the black hole, and I can get you somewhere else. But what I can't do is I can't clone you. I can't take a literal clone of you and make you somewhere else. So I can't, like, if I knew all the information that made up Eric Jennings, you're not like, black hair, blue eyes kind of thing, or blonde hair, blue eyes. But I'm talking about like the orientation of your molecules and how they behave and how they're going to behave. And I can take all this stuff. If I had all this information about Eric Jennings and his molecular makeup, people want to think, well, that means I could clone you somewhere else. And so that's kind of the thing. Like, let's say another idea for teleportation is I put you step into this capsule reads all that information about you, and then this sends that information to some other capsule, and then it recreates you, or whatever the sci-fi term is for that. It clones you and makes you in this new capsule. And so that's another idea. Can't happen. It's been proved it can't be done. There's literally a theorem called the no clone theorem. It is impossible. You cannot be cloned. You can't clone macroscopic things, and you can't clone even molecular things. You got to go through the physics test. So there's no like layman's term for explanation.
So the math. Say, because people think like they clone cows for beef and stuff like that.
Yeah.
It's not.
Yeah, that's like genetic cloning. Yeah.
So I guess, if you understand the difference, can you like go into a little bit? Because for me, a clone is a clone.
Yeah.
So you're speaking about a very different thing.
Yeah. So genetic cloning is like you're trying to clone the DNA. And even if I don't know enough about genetic cloning on like the how it works, like the ins and outs, but I do know you're trying to replicate the same DNA and get the same sort of outcome. And even those clones, like, they come out looking different, right? They look similar, but there's differences. I forget even what the first like clone sheep ever was. I forget. I think it was Dolly or something like that. You remember that? Yeah.
The sheep.
Yeah. But even that sheep like looked different than like where it came. I'm not even sure if I remember it looking funny, and so I just assumed it would look different. But you can clone other animals biologically, and you can even molecularly tell there's differences. And so you can measure differences in these two people. They're close. They're clones because based on the cloning of the DNA, but they're molecularly different. And I can point to distinct differences. One maybe even taller than the other or whatever. But when it comes to quantum mechanical clone, like, you can break this down something really, really simple. Like, I want to clone a certain atom, right? And atoms are all pretty fundamental. Like a helium atom is what it is, and you can tell what it's are, but there actually are differences, and they're measurable differences. And so the idea here is I'm taking the exact replica of this specific thing. And what goes into defining what something is are the behavior at the quantum level. And if you want to, you can do a math problem. And so that's how I was convinced of it. It's hard to put in well, it's hard for me perhaps to put into lay terms here why it doesn't work. But once you go and see the math and work it out yourself, you'll see that you literally cannot clone something at the quantum level, which then means you can't clone something at the classical level, which is just more aggregate quantum things, right? So it's just impossible to clone the state of something.
Like, well, not state of matter, but the matter of the, like what it's actually physically made of.
Yeah, state is a quantum colloquialism for basically the identity of something. Like a state is what is the essence of what something is.
Yeah. Gotcha. Yeah.
Yeah.
This is awesome though. I feel like I'm learning a lot and I'm going to be very confused for the next week.
Yeah.
But
we're all still confused.
It's good though. I think. All right. Well, I guess we might as well just move on to the next quirky thing. You got time travel, did teleportation, parallel universes. What else is a quirky sort of, I don't even know.
Yeah, so I'll tell you a little bit of my research. These things are called weak values, and
okay.
I run the risk of talking about something I'm super passionate about because this is what I spend my day-to-day doing, but it may not be interesting to others, so I'm just going to be careful and tread lightly. So I'll tell the cool stuff about it.
No, you're good. I appreciate the segue because I had no idea what to say at that point.
Yeah, so these things are, so weak values is new. Okay. Lev Vaidman and Yukio Aharonov, who actually was the lead author and came up with the idea. I think Lev just helped out with some of the math and helping Aharonov think through this. I hope Lev doesn't ever see this. He probably doesn't like me very much. But so they came up with this idea of weak values, and what they discovered was
weak as in not strong.
Yeah, WEAK values, and they just called them that because of what you'll. I'll explain why they call them that in a second. But first, the seminal paper, the lead paper, I think it was titled, and I probably should have this memorized because it's like the seminal paper of my entire body of work so far. But it's like how the spin of a particle can come out to be 100. And spin is a fundamental measurement. It's like the color of your hair of a particle, and it's just a property of a particle. And they can only be with certain things. Half, negative half, and they certainly can't be 100. And that's what they showed. That was the title of this paper, and set the world on fire for a little bit. The quantum measurement world, and that's what this is a type of quantum measurement. It's something you can observe via doing a quirky way to measure things, and so what they end up doing is, and what this really is going on here, at least what I think is really going on here, or a way to describe it is, let's say that, okay, here's a simple example. So I got a couple, a game, the cup game, like I've got there's like a ball or a peanut or something like that, and you've got like 3 cups, and you lift up one of them, you show it's under this one, and then you cover it, and then you shuffle these around. Okay, I shuffle these around a bunch, and then like I have you pick which one the ball's in, and you pick up all of them and they're gone, right? Well, that's magic because somebody did something weird to like move it out of the way, and now it's on the floor in his pocket or something like that. And that's what weak value measurement is. It comes out that the weak value can have values outside of what is expected. So the ball will end up in the next room somehow, if you look at it, if you look for it in the right way. And what that means is, and this is the weak part, you can only get it by performing a weak measurement. And it's a certain like a recipe for getting this result, this weird result. Okay. So a traditional, I can't use the word classical anymore, a traditional quantum measurement, because this is like new quantum, right? So this isn't even stuff in textbooks right now. It's in some books, but if you pick up it's not in my quantum textbooks I learned in school. So this was, I had to learn all new stuff. When you perform a quantum measurement, and the foundation of quantum mechanics is this measurement. When you look at something, okay, what you're doing is you're breaking down the wave function and collapsing it into a certain state, the essence of what it is, right? So things behave statistically or quantum mechanically in wave, and they're described by wave functions. It's just a mathematical model. We're not going to do it. It's just a mathematical model that's kind of funky, that behaves statistically like a wave. And then when you go and you look, it behaves like a particle. That is to say, it is somewhere. That ball is under one of these cups, and performing a classical quantum measurement, I look under one of those cups, and the statistical behavior of it existing in all three of those cups breaks down into a single existence, and voila, the ball is under one of these cups, right? So summarize one more time. You've got three cups, the ball is under one of them. Mm-hmm. From quantum mechanics, before I look, I know that there's different probabilities. It's a probability it's here, it's a probability it's here, it's a probability it's here. And to say that it is, most people like to think, okay, that means that the ball is under one of these things. And classically, it is under one of those cups. But quantum mechanically, it's not. It's under all three of those cups to different levels of probability. And but it exists under all of those cups. Or, there's debate about whether you can make that phrase, but there's also no way to prove that that's not true. So the ball you can think of is actually existing in all three of those cups. And when you go to lift one up, that's when the measurement takes place, and the ball now switches, the physics of it aggregate to exist in a specific state that was created by your observation. You're basically breathing that ball into existence by observing. Okay, that's how quantum measurement works. All right. If I did that experiment enough times, the probability of like the three different cups would even out to, okay, so if it was 25% here, 25% there, and 50% in the middle, if I measured it 100 times, you're going to get roughly something along those numbers. Okay. Weak values. So I know this is we're not doing any math, luckily. So hopefully it's not too out of grasp.
No, you're good. I think I was following that, especially the way you described the probability of existence.
Yeah.
That makes sense. It's almost from the standpoint of like it exists under all of them quantumly.
Yeah. Yeah, that's fine. Yeah.
But doesn't exist classically until you see it there.
Bingo.
Because of the probability that it
that's right
be under any of them.
Yeah.
I got you.
And this weird thing of like looking and not looking, it only really occurs on the quantum level. So they joke about like the cat. You know the thing about Schrodinger's cat.
Remind me.
So someone's calling me. Just want to make sure we're. What's going on? Oh, I'm getting FaceTime. That's what it is. Not today. All right. So look. So the Schrodinger's cat thing, which everyone kind of likes, it's a popular science thing. This cat is, the whole experiment is, this cat is like, let's say this cat is in like a box, right? Mm-hmm. A nice box, it's got AC, like it's not, suffering. Box, the cat's chilling in this box, okay? But also in the box, in this nice AC box, is a vial of poisonous gas, okay? They had to set this up like this because things only behave like this at the quantum level, but they're trying to like draw a correlation to like the macroscopic level. Mm-hmm. So they used a cat. I don't really know why. I think maybe this is maybe like cats. For some reason, physicists like cats. I like cats, but I'm allergic to them. Just a disclaimer. So this cat is in this box, and they want to try to give it some quantum like existence, right? Either it's alive or dead. And how it does this is this. It takes this vial of like poisonous gas, right? And in order to break the glass or something like, hold on. Yeah, there's like there's a couple different ways to do this. Actually, I think Einstein, the original proposal was like this bomb that went off. Okay. So,
Something that could kill the cat.
yeah, from a probabilistic perspective, like a decay, that's what it is. So atoms decay over time. Atoms further down the periodic table decay faster, and certain properties like uranium, plutonium, things like that. And so the timing of this decay is weird. So let's say after a minute, the probability of this atom decaying and breaking this glass and causing this poisonous gas to break into the box and kill the cat is like 50%, right? So after a minute, there's a 50% chance that the atom decayed and broke the seal and killed the cat, and 50% chance it didn't. What people are asking is this question. This is the thought experiment that kind of like gave him all this acclaim. So is the cat dead or alive after a minute? And not just like, okay, we understand, we can easily say there's 50% chance it's alive, 50% chance it's dead. But the question is it actually alive or is it actually dead? And it's just that we don't know until we look, or is it alive and dead? And this is the whole measurement question in quantum mechanics. And you can say with some confidence that it's both, and it's not actually one or the other. It doesn't get decided until you actually observe it. And so that's a wild thing with quantum mechanics. And that's kind of the same thing with the ball, and it's not decided until you look at it. But what you're doing when you lift up the box and look to see if the cat there is you're breaking down this wave function, this probabilistic behavior. It breaks down, it flattens out, and there's no longer a probabilistic spread, and it's 100% certain it's either dead or it's alive.
Is that what you were talking about with the slit in the wall earlier?
That's right. Yeah, you're looking at that's right. Yeah. Dude, you're a quantum physicist ready to go. So
I don't know about that.
So the trick with weak values is weak values come along, and it's not the ball isn't in any of those cups. The cat isn't dead or alive. It's some other weird state. The cat's a bad example because it's a binary thing, but the ball being in a cup is somewhat helpful. So the ball is either in one of these three cups, statistically, and then when you go to look at it, it screws that up and it firmly is in one of these. But with weak measurement, you're peaking. You're not actually lifting up the cup and looking, like lifting it up fully and looking at it. You can think of it as you're peaking. I'm gonna lift the cup up just a little bit. I'm gonna see if it's in there. Okay. So you're not breaking down the wave function. You're kind of fooling with it. I'm going to look a little bit, but I'm not going to look so that it's not a strong enough measurement that I break down the wave function. It's a weak measurement. I measure it very weakly, just very subtle interaction. A good example of like something we do is like a laser beam has a spot size to it. So I'm going to make sure we don't get too crazy with this. I'm going to try my best to do this layman, because this is really this is more along the lines of what experiments that I actually did. Sure. Laser beam has a spot size to it, right? Mm-hmm. All right. Let's say that I want to translate that beam one way or another. Like I'm doing it via a crystal that like I put a piece of glass in between, and I like tilt it a little bit, and that kind of like off centers the beam a little bit, right? If I had a big enough piece of glass and it's got a big enough index of refraction, that light's going to move through that a little bit in a weird way. I mean, that's just how light works, right? So, but the point is you're moving the laser beam over a little bit, you're translating it. So you have this beam spot size, and you can translate it a lot. When you translate it a lot, and then you look to see where it's at, you can say, okay, this beam moved over here by some amount. Well, at the quantum level, the location of photons, particles of light, have a bit of uncertainty to them. You can't tell specifically right where they're at, right? At least if they have a known momentum. Okay. The point is they've got some uncertainty. So it's not just a fixed beam. There's also some area on the edge where it's like, well, I'm not quite sure. So if you translated this beam in such a small distance, if I just wanted to translate it just a little bit to where like the new location is still largely overlapping where it originally existed, then it's still within the quantum uncertainty of the existence of the original beam. Then you can't even tell that you're not actually, like, this is the weak part of the measurement. It's still within the same uncertainty. And I know that's not the best description. I don't think I've ever attempted to describe this in like a simple way. This example.
Sure.
but that's at a macroscopic level of actual experiment observing light in a weak way. That is one way to do it. And how much you can still measure, but I can measure so that you want to measure how much did you displace it, but you can't transduce it. You don't have pixels small enough to say it moved by some, the width, less than a width of a hair, right? It'd actually be a lot smaller than that. We're talking about like femtometers and picometers, like things like times 10 to like a meter times 10 to the negative 14. You don't have cameras small enough to transduce that displacement. But if you measure it in a weak way, what you can do is when you go and look, so you got to do this other weird stuff. You got to put a polarizer in the front, polarizer in the back, and kind of like erase the witch path information or the Welter information. And what you end up with is that beam that you translated only slightly is now way the hell over here. And so when you go to look, the beam is like multiple meters away from where it originally was. And based on how far away it moved, I can use weak value theory to tell you how small it actually moved. So again, a weird thing that I usually have slides in front of me when I describe this. Yeah. You translate the light like a picometer, something so damn small. But and that's actually how much it's moving. But when you do this weird trick before and after, and I won't describe it, then what you end up getting on the detector, if I'm looking to see where the light actually is you get a large translation. And so now, again, that's that whole, it didn't appear under one of the cups. It's now in the next room over for some weird reason. And it's because you measured it weakly and you did this weird prescription of pre and post selecting, which I won't describe, but that's what my research is around. And we are trying to figure out how to apply that to enhance sensors, you can say radars, optical cameras, things like that. So
okay,
the Navy is interested in that sort of thing.
Seems like something they would be interested in.
Yeah, right.
Let me try to.
So that was probably not that good.
No, you're good. I think I'm not going to say I understand, right? But okay, so you've got the wave function. When you don't interrupt the wave function using the ball under the cups,
yeah,
all the cups are down, and it exists in all of them with some probability. When you pick up the cup all the way, then it's either there or it's not. And so, but when you go in between, instead of it being there or it's not, like you would think of it physically, like the classical physics way, when you mess with it just a little bit, it just offshoots somewhere.
Yeah.
Or can offshoot somewhere.
Yeah, if you do it the right way. Yeah.
Yeah.
Yeah, if you peak in the right way, it does something nobody would expect.
It's almost like the wave function is going, and instead of like stopping it, like full send stopping it, you kind of just like push it or like mess with it, and then it just like goes haywire almost. At least, I don't know. Is that a stupid person's way to describe?
No, it's like before while the ball is under one of these three cups, statistically, people don't know what it's doing. We don't know what it's doing. We can't say that it's definitely in one of those cups. We can't say that it's hard to even say that it's exists in all of those cups. That's the most fun thing to say, and it's okay to say that because it's not really inaccurate, and that's what most people say. But the answer is we don't know what it's doing. But what we did find out with weak values in 1988 was that when you go to look and you it's like this you're like walking into a house and you don't know what to expect. You know that but like you creak open the door, like it's like your kids down or cats like playing around your house or something like that, like knocking shit over. When you open the door, they look like they're not doing anything, right? But when you peek and you don't let them know that you're looking, they're doing crazy shit. That's what's going on in quantum mechanics. When you lift up the ball's going to behave me like I'm a ball. I've just been under this cup the whole time. But if you peek in the right way and it doesn't know that you're peeking because it's still within the uncertainty of quantum mechanics, if you peek in the right way, it's doing some crazy ass shit. It's like it's not even what we would predict, and so that's what we've discovered with weak value theory, and it's fucking awesome. It's cool. It's wild.
This is telling us then that when the wave function is still going and we've not peaked, we've not looked, that it could be doing anything.
Yeah.
Actually.
Yeah, and it'll behave the way we want it to if we look in a very deliberate way. But if we peek and do this weird looking, then it no longer behaves via this weird wave function. It does something else that weak value theory has had to build out that behavior, and that's what we do.
Gotcha. So let me ask you this question then, and if this question makes no sense, then please feel free to tell me. Is the weak values kind of a stepway into observing? So like being able to, I'll say, put like an X-ray through the cup to see what the ball is doing in that example. Does that make sense?
Yeah, no. So like, first of all, when people who aren't familiar with this stuff start to ask questions they think are dumb, that's usually when like, big discoveries are made. People that are like live in this world 24/7, they don't even think to ask some questions like that. I mean, it's a good question. And I would say yes, but it seems as though that's not somewhere the community is going. The community is going and trying to figure out how to apply this stuff, and they've done weak measurements in all sorts of different contexts and done some other weird stuff. But I'm not actually, you know what? Let me correct that answer. So first I was going to say that I don't think that, because what you're asking is like, are we using weak values to like
is it like a stepping stone
understand how things are behaving more fundamentally, being able to see through the wall, because this measurement thing is really screwing with us. So if we can get around that via weak values, maybe we can learn more about the system, and we all are trying to. But really the fundamental, so okay, so have weak values uncovered anything weird and new besides this whole it behaves in a weird way afterwards, right? And the answer is yes. So in fact, Parks, the guy who I mentored under, so I was the mentee of, Dr. Parks, he, along with Scott Spence and John Gray, in case anybody's listening, just to give credit, these guys discovered possibly what's called retrocausality. And what this is like backwards action. So this is like this traveling in time kind of stuff. So we don't have many examples of this. We don't have any examples of this, except for in some retrocausal things. And so let me try my best to explain this. I don't think I've ever explained to someone lay terms. So I'm going to try to do it in an analogy rather than trying to describe a Mach Zehnder interferometer. So an analogy.
That's why, before you go, that's kind of why I like doing this. So if you're trying to explain, I'm trying to learn something, and maybe we're like, I can work it out. You tell me where I'm wrong, and then you work out how, like, so the next time if somebody random asks what it is, then like, you know how to explain it, and I've learned something new and everybody's happy. Yeah. So the Feynman method of learning something is like, I pick up a paper, read it, try to go find someone to explain it to them. And as you try to explain it to them, they will help you work out what you don't know about it. And then you go and teach to someone else. So that's the Feynman method of learning. It's fine. Richard Feynman, dude. I didn't actually know that was a thing. Well, so yeah, there you go, learning something new. Yeah. All right, go ahead. So retrocausality is when something that you do down the line. So, all right, something that'll seem unreal. So I've got a window here. If a ball came crashing into this window all of a sudden and landed here on my desk, that window's broken, the ball's in here, damage is done. But if retrocausality is saying that, no, that's not true. You can undo that window being broken if you do something in the right way now with this ball. So if I do something to the ball so if I can fool with it weakly, if I can measure the existence of this ball in a weak way, if I don't see it, but I can measure it in a weak way, you can affect what it's done in the past. I can make it so that ball never came through that window. And this is the essence of retrocausality. You're looking and observing nature at a certain point in time, and what you're doing is you're affecting the behavior of it from the past. And this has only been demonstrated. The ball through the window thing is a macroscopic, analogy, but it's only been done with light and very small distances. But it seems as though it's very true. I say very true. Probably a heavy worded way to say it. Possible. There's no other explanation for it.
right now. So it's not been challenged in a convincing way. So far it stands as an unexplained phenomenon. So that's what retrocausality is. And that gives people lots of hope. And that's where the people start to get wired up again, like, okay, so we can do stuff with time, because right now kind of it's untouchable. Time just marches on, but maybe it's a little bit deeper than that.
Yeah.
Yeah.
I feel like that should just stay with you guys. Those regular people should not be. You get people doing some weird things, man.
Oh, I know.
All sorts of stuff. But no, that's really cool. So, okay, and this has been, I guess, demonstrated with light in a lab. So if the light, I'll just say moves in a certain direction, and you mess with the wave, like you peak, essentially. I'm using that analogy, and you peak.
Yeah.
You can make it go back to what it was.
Yes.
Ish.
Yeah. And I even when I first got there, I proposed an experiment to test some pieces of this, and it was really freaking hard to figure out a thought experiment to test this weirdness. And it's very tough to wrap your head around what's going on. There's you don't have total freedom to do whatever the hell you want to do. You can't make people not die again, right? But and that's the thing, is people then take this and they say, oh, we can reverse time, I can make I don't know, JFK come back to life, something like that. And it's it doesn't unfortunately it doesn't work like that. We can't do things that wild. And that's where you lose listeners, because they want to hear that it does crazy stuff, but it's really specific things you can change.
You can't really, that gets into the biology of stuff, and you can't really biology, at least in the same, it's not been played with in the same sort of way.
It's a simple thing. Yeah. You're able to affect. I can change. Basically, one thing you can do is you can change the momentum of photons. So if photons are traveling in a path, a beam of light is traveling in a path, and I'm measuring its momentum around point A here, and then I do something up here. I do a weak measurement at point B. Then that momentum that I did measure, it changes, and now it's saying that all of a sudden these photons didn't have that momentum, and it's but I just measured it, and it said it does. And so you got contradictory measurements, and the only way you can explain it is by working back in time and saying, okay, cool, the quantum theory does actually explain this, but the only way it's explainable is by saying that time was reversed and you had back action. The effect up here at point B changed what happened at point A, and that's what retrocausality is. And it's so simple. It's such a fundamental thing. I just slightly change the momentum. You can let your dreams get the best of you and take off with that and say, oh, well, I can, then, reverse some weird interaction that happened at a macro scale. But I don't know. Maybe, but it seems as though so far what we know about quantum mechanics and stuff, those kinds of things don't translate to the macroscopic world. Teleportation is really freaking hard. I can't weekly measure Eric Jennings, and all of a sudden in one life he's Cristiano Ronaldo. It doesn't translate to that.
That's okay. So when you're researching this stuff and you're in such a small scale, how do you actually go about researching that? Because you have a microscope, but you can't really see a wave function with a microscope. So how does that work? And also, does this get into particle accelerators? And if so, what actually are those?
Yeah, so we'll have to go down that road because I don't deal with particle accelerators right now. We do. So laser light is coherent light, it's classical light. But at the fundamental level, that laser light is a bunch of photons. And what we do is we call that an ensemble of photons, a group of photons, like an entourage of photons. And you can treat a group of photons as one quantum system. So it's an analogy to, you can say it's one single photon. And so you can draw the analogy, and that allows you to play in the quantum realm without actually having to measure single photons. The particle accelerators let you do that. So you can start to get weird things that are happening. And it's what's weird is like in these particle accelerators. So what a particle accelerator is you're taking not photons, because you need things with mass, and so you're taking like atoms. You could take it doesn't really matter, copper atoms and things like that, and rubidium atoms, and that's what a lot of atom interferometry is. But this is slightly different atom interferometry. This is accelerating atoms around like a racetrack. There's racetrack designs. There's cyclotron. A cyclotron is like it was invented by oh man, my science history is a little rough here, but there was a gentleman out of like Caltech, and they had this cyclotron, and there's Berkeley, California, Berkeley, and I think Caltech were like competing pretty heavily for a while. They were like these particle accelerators. And what you do is you're getting these things up to really, really high speeds, really, really high energies, like near the speed of light. And so the speed of light, as we know, well, as maybe people know, is the ultimate fundamental speed limit of the universe. Nothing can go faster than the speed of light. And which is a wild, wild thing to wrestle with. I remember wrestled about as a high school. I'm like, why is that the fundamental limit? And the answer is we don't know. Like, why is it that number? We don't know. We don't really know. Why is the fundamental constant of the universe? Why is that what it is? You know, we don't know. And this is where people start to get in like, well, then, you know, there's definitely an architect, you know, and I mean, you know, sure, but as scientists, we just try to understand and measure with the stuff. But it is fun to think about that, like, why is it that number? But anyways, so we've got this ultimate speed limit we're trying to get things up to, and it's very hard. You have to put a lot of energy into it, and it just, they use like magnets and magnetic fields, and the magnetic fields affect the atoms in a certain way, where as they're going around this racetrack, it's just constantly accelerating them. They're picking up speed over time. And it takes a while to really get to that and to get things right. And particle accelerator experiments are pretty freaking crazy. They're cool shit. The one we have in Virginia is the Jefferson Particle Accelerator. And I don't know, there may be some fancy name for it that some donor got, but the Department of Energy runs experiments out of there. And what they end up doing is you have these atoms going around a racetrack, and then you can either you can set up a breakaway to where things are going on this racetrack. Eventually they break off. So something like that. So it's going around and around and around, and then all of a sudden it breaks out, right? Well, you could break out and you could put something in the way. So I can put a wall there and it smash these into some stationary things. You could, whatever you'd like to do. I mean, you can test lots of different materials like this too. But a lot of times what they'll do is they'll have a complementary racetrack. And so you have something that looks like this. So, and I'll just do a new thing, but you can imagine you've got another one next to it, another racetrack next to it, where it is doing the same sort of thing. And they are then going to exit and smash into one another. So something like that. So if you have one racetrack and another, and then they both shoot out and they collide into one another, and that'll give you particle collisions. And there's lots of other ways to do this. That's just a rudimentary, easy way to understand it. But you get these things up to near the speed of light, really high energies, and you smack them into one another, and some crazy shit happens.
I was about to say, that seems fairly destructive.
Yeah, so you get that's what people were like worried about, is you get really, really, really high energies. You're taking really high energies, other energies, and combining them, and you get much, much higher energies. And so, like the Large Hadron Collider, LHC, it's a big particle accelerator. Like, I think that's like Switzerland or Sweden or something. Unless Chuck, by the physics professor, probably smacked me for not knowing, but it's one of the two. And there's this giant thing, tons of energy in these particles. We're looking to explore new things. We're looking for like the carrier of mass. So this, the universal theory of physics is still the golden nugget that people want, and they're hoping that the LHC, Large Hadron Collider, could get them there. They can discover like the God particle, which they did a few years back, or not a few years back. I mean, well, yeah, a few years back on the time scale here we're talking about, and it just. One of the ways that particles, like, we didn't know how particles carried mass, and so like they found that they're looking for this particle that's responsible for the transport of of mass. And so that's what they found with this. But when they were setting this up, people were really worried about them creating a black hole. And you get enough energy in one space, you can create that singularity we're talking about. It's like, okay, so you create this black hole and then everything sucks into it. And you think that this is like some, yeah, people are worried about this, whatever, like scientists know. I mean, it was really hard to like convince that wouldn't happen. There's lots of questions like this throughout history. When we were making the atomic bomb, one of the questions that was brought up that was hard to explain was, if you create this atomic explosion, is it going to like cause like solar winter, or I'm sorry, atomic winter, and like burn the atmosphere, and then we all die? Not just the atomic winter, but like, I think it was one of the things, like catch the atmosphere on fire was one of the questions. And could it catch the atmosphere on fire, and then we're all screwed? And it took some time for scientists had to address this question beforehand. It took some time to really answer and say, no, it's not possible. And the same thing with LHC. People brought this question up, the board members, most people that are like funding this sort of thing aren't scientists. And, they've got they create a black hole and like some crazy shit happens. They got a lot to answer for. And so they had to get this stuff answered. And that was it was an interesting, like, I remember hysteria going on when that was first created. It was the LHC, and that was a question they were worried about. But no, so particle accelerators, what's cool is what they've been able to do is look. So it's actually like the number one source of data for cosmologists, these people that are trying to understand the universe and the history of the universe and how far back in time, and trying to measure the radiative background and the cosmic ray background. And they get a lot of information and data from these particle accelerators. Excuse me. So one of the things that's so cool, and I'll just cut it off here. But one of the things that's so cool is that, at least I think is cool, is these particle accelerators. When it first started out, I mean, we got pretty high masses, pretty high speeds, pretty high energies, and we're able to see like kind of backwards in time. So these cosmologists are trying to understand like the origin of the universe, the Big Bang, right? This kind of idea. And in order to study the Big Bang, they needed to make their own Big Bangs, their own collisions. And as they got better and better and faster throughout time, we started to be able to work back further and further, closer and closer to the Big Bang, the origin of the universe. So that was interesting. It's like we're getting higher and higher energies in the lab, higher and higher particle accelerator speeds. We're able to look further and further back in history and in time and understand like the origin of the universe. And I thought that was a cool little correlation. But
that's awesome. That's wild.
Yeah, it's interesting.
In so many ways. The black hole. So the question about the black hole is the energy that creates a black hole, like just out and whatever.
Yeah.
Like, that comes from what would be like an exploding star, essentially a supernova, right? Kind of, or is that one way?
Yeah. So, let me think here. So, I don't think there's not necessarily enough energy to. You could think of it like that. The Big Bang itself is such a unique event that it's
just a black hole in general. Like when they were worried about them creating the black hole in the lab.
Yeah, that's where because the whole Big Bang thing is there's so much mass and energy in this one singular point, and all of space is wrapped up into this, and then all of a sudden it explodes and expands and inflates. And this is I think it's like the new theory, like inflation theory or something like that. And all of this weirdness is happening. So the closest relative we have to that today is something like a black hole. Yes. So the closest relative is that, but they're still so different. But in order to better understand black hole, the Big Bang theory and all that, yes, we look at black holes and we relate them. And that's where like the mind goes when you say, well, we're going to smash things in at really high speed. You're like, well, but could you create a black hole? Because there's a lot of energy in a very tight point that you create a singularity. And that's a valid concern at its face, and then you can go look at it and actually measure, is it possible to create a singularity? And that's what they had to do. But yeah, that's right. It's not inside of stars necessarily, but the black holes for sure are analogous to behavior you get when you start smashing things into one another at very high speeds.
So we don't have the capability to smash things together at like to get the energy necessary to create one of those.
Yeah, correct. Yeah.
So would the caveat then be yet?
Yes. Yeah.
Oh, good. Can't wait.
Yeah.
Can't wait for that one.
Yeah,
Oh,
it's
geez.
we can't create enough energy here on space. I'm sorry, on Earth in a lab to do those kinds of things. We can get damn close, but the caveat is very much the cloud hanging over our heads is the yet for sure. Yeah.
Geez, that's just wonderful. Isn't it?
Yeah, you get
Well,
scientists that say it's not possible to do it, and we can't create enough energy here on Earth to do that, so it's never going to happen. But
I would think though, even if we had enough energy to create a black hole, then all of us would die in the first.
Yeah, I
explosion
mean,
anyways. So like, not that we would ever. I mean, the outcome of us is not really.
we'd just be speeding it up anyways. I mean, we're all going to die at some point. You get the ultimate heat death of the universe. That's like an inescapable fact of thermodynamics. So I mean, I don't know what everyone's so worried about. We're all going to die anyways.
Oh, jeez. So, speaking of cosmologists, people that do like thermodynamics and all that sort of stuff, so obviously all these worlds and these fields are intertwined. By worlds, I mean fields, like your world that you live in of quantum physics.
Yeah.
They're all intertwined in some way, shape, or form. Do you work with people from cosmologists or other people from other fields often, or are you kind of just like only when you like, I guess, conferences or whatever the case may be, or do you work with them often? Because it's very easy to get wrapped in, like we were talking about earlier, it's very easy to go in sort of a religious direction or a cosmologist direction, like it seems. So do you kind of sit in your quantum physics world, or you bounce around?
Yeah, so good question. If I had it my way, I'd engage with them a lot more, because that means that I would be doing a lot more of the fundamental research. And so this year, Ben Baldwin and I, who's one of my researchers, who's an all-star, by the way, he and I developed some theory, and so we expanded the quantum mechanics, the theory of quantum mechanics, to cover some weird behavior we were seeing. So we participated in and actively advanced the theory of quantum mechanics, making us theoretical physicists. And with that, you get some weird shit that happens. And so you get these people that don't need a application. So we have to do it. The only reason we get to do it is because I can point to an application and say, let me look at this and pay me to do this, because I can possibly get you something better than what you currently have in terms of like a system, like a gun, shoot further, whatever. Right. But I have to do that. And it's hard to do. But what these guys do is, once you start to put out stuff like that, like Parks was putting out stuff about dark energy and retrocausality, that's when you get the cosmologists coming and sniffing around and looking and asking questions, and you know what I mean? And so we do engage them every once in a while. I met Lev Vaidman, Yukira Haranov is interested in this foundational fundamental stuff. And there's lots of crossover. But we don't get paid to think about these philosophical questions, because knowing whether or not that ball does exist or does not exist before you look at it doesn't give you better sensors, and the Navy doesn't give a shit about it. So I don't get to actively work with those guys often, but when you do make good discoveries and do build out good stuff, they do come sniffing around, and you do get to engage with them. Yeah.
That's awesome.
Yeah.
Sounds like incentive for you. Discover more shit.
Yeah.
You'll get to talk to him. Real quick, before we've been talking for almost 2 hours at this point, and I know it's Friday night. Yeah, man, it's Friday night, and I know you're probably super busy, even though you said you weren't, and I don't really believe you. That's all right.
Dude, it's a mess, man.
Have you ever watched The Big Bang Theory, the TV show?
Yeah, my parents loved it, and it was like, whenever they watched it, they would like, well, not always, but I'd get a text like, "We're just watching Big Bang Theory, thinking about you."
So, all right. So I have two questions that are associated with this, and they're the questions are not related other than the fact that they both stem from that show.
Okay.
They talk about string theory often.
Okay.
So if you want to describe that a little bit, if you know, I mean, I'm assuming you know something about it. And then the second one is, are the concepts and stuff that they talk about, like, I guess, to boil down the question, does the show piss you off because it's unrealistic? Essentially, are the two questions.
All right. I'm going to disappoint you. I don't know enough about string theory to be able to layman's terms it. I'm familiar with some of the math. The universe being wrapped up in these little tiny vibrating strings is kind of the idea. It's very hard for me I don't know enough about it to be able to go further than that. I tell you this, a couple of years ago, so string theory is no longer like the popular cosmological, like where the universe came from theory, the unifying string theory is an example of like this unifying theory thing, right? We're going to attempt at it.
Right.
There's a better one now, let's say better, and let's just be careful though, because there's lots of debate in this stuff. But the more popular one now is M theory. I think it's what's called, but there's variations of this. I think it's like M star or M plus, like it's kind of like a coding language. Just they upgrade it every once in a while. And that's kind of what they're doing with string theory, but it's kind of all based on this original piece. But it's very, very, I mean, you don't have to have any intuition about the physical world to work as a string theorist or a cosmologist. You just need, I mean, not like Einstein where he like felt these things, and kind of wrote them down. You just need to be very good at abstract math. I mean, to be able to understand and say what this math means is really freaking hard. And you have to have a very good brain. And that's what these guys, these string theorists and M theorists are capable of doing, is abstract math and to be able to like say what that means. I mean, once you get into like higher dimensions and things like that, you'll see like that's where people's brains do start like hurting. It's tough. And
sure.
I unfortunately don't know enough about string theory to be able to describe it in a way, but I know it's like talking about vibrating strings of energy, and that's what the different universes are. And I wish I could give you some more. I apologize, but Big Bang Theory question is this. It's a good show. It's funny. I don't think I've ever been like, I think when I was a kid, how about this? This is probably a better answer. When I was a kid, when I was younger, I was probably very poo-poo. And so that's why I kind of always felt like a bad taste. Like I look at that stuff and I'm like, these aren't real scientists. And, they kind of make some lame jokes and they say some stuff and I'm like super critical. I'm like, oh, this is kind of wrong. They had a real, but in truth, Big Bang Theory had a good like crew. And I've talked to a professor about this since this. They had a good like science advisor and they got a lot of things right. And we even had fun and like I was the president of the Society of Physics Students School back in the day. And like we looked through this stuff afterwards. There's people sitting around and talk about this stuff. And it's like cross-reference some of their claims and they're right. Like they would go through good lengths to try to make the science right. So I think they did a really good job. I've got no problem with it now, but I'll tell you this, when I was younger and I was like, when I thought I was smarter than I was and we're a bit little arrogant and you start to get into the science world and you feel like you don't know that you can't clone something, like you get that arrogance right away and it's stupid as shit, but a lot of people go through it. And I think that I had that when I was first encountering Big Bang Theory. And so I've got a bad taste in my mouth about it, but I grew out of it for sure. It's a good show.
Yeah.
They did a good job with all the physics.
That's what, that was my impression of it. Obviously, not being a physicist or anything.
Yeah.
It seemed like they had gone to some effort to make sure they got some stuff right.
It was pretty solid from my understanding.
Yeah. All right. What's next for you? Are you still a PhD candidate, or have you got it yet?
No, so I'm still a candidate. I'm going to get I'm in a PhD program, but I don't even have a master's yet. I should have that this winter. And then I've got to take the qualifying exams and move into PhD candidacy with talking about probably weak values and stuff if I stick in it. But I'll tell you what, I'm considering just grabbing a master's and getting out of there. I mean, I am already the team lead for the quantum technologies group at Dahlgren, and I feel like that experience, if it works out and I can leverage good research there, then I can take that experience anywhere with a master's, take that experience anywhere, and kind of don't need the PhD. Because I'll tell you what, if I can do that, I mean, even one of the smartest men I ever met, and most popular men, he was actually Freeman Dyson. He trained under Dr. Richard Feynman. He kind of came into this speech. I listened to him talk, and he came into this thing, and he said, like, if you can do all of the research you want to do in life without getting a PhD, do it. And he like shocked the room. I mean, this is like people get the PhD world is a very good old boy world. You know, you got to get a PhD. You know, that nobody gives a shit like how much work. Like, you got to do it. I don't care. It's hard work. That's what it is. And they intentionally make it hard and are like, if you're like, man, this is tough. Okay, that's what it is. And I'm like, well, I run a research group. Like I've got research projects going on there constantly. It's a 40-hour job and then some, especially in certain times of years like right now. And, you know, it's very hard to get all my homework done and stuff and still do good research. And it's like, so what? Like, that's what it is. It's tough, man. It's a pain in the ass. And I'm becoming slowly disenchanted with the whole thing. And I think that getting out of there with a master's and reclaiming my life back, and as long as I can still achieve all of the professional research goals that I want to achieve, which I think I can. If I realize I can't, then yeah, I'll go back. But if I can, which I think I can, run this lab, and you know, kind of my goal is to continue to run a research group, put out good research, and engage with and mentor like good scientists coming up, I also want to be able to, like, you know, kind of advise a little bit too. So science advisement is something I'm interested in as well, which doesn't require a PhD. Masters and a ton of experience get you in the door. Running a lab, you gotta have a PhD. I run a very small lab, a very small group, and it just kind of like fell into my lap when Dr. Parks retired. And we've been under the radar, we've been under the microscope a lot since he left. And they're looking at me like, you better get this PhD. You need to, in order to be able to be in this role. And I've been in the role for a while now, and I feel like we're doing pretty good. And if we continue to do pretty good, and I got a master's, you know, I don't necessarily see why I need a PhD. So that's what I'm hoping for. I think I'm going to take a little bit of a break. That's my goal, or that's where I'm at right now. That may change. I'm kind of second guessing it. I'm like, I might as well just get a PhD. So I don't know. I'm day to day on that one.
Yeah, makes sense. Especially if you're feeling that way about, you feel like you can get all the research you want to without it and stuff. Academic world is it wasn't for me, but
yeah,
definitely the people that I know that stayed in it, like Dr. Chris, who he was on episode 40, got his PhD in immunology, and then
I saw a little bit of that.
Yeah, so it's definitely the people that stay in it that I know are super bright. And I think, I don't know, it was always meant to be a good thing, and I think it still is for the most part, but there's been some, I'll say, warping of how it actually works, I feel like, at least from what I've heard. But
there's a deeper conversation in there for sure.
It is 100%. Look at this. We were supposed to talk about so many things, and we spent 2 hours talking about only quantum physics.
That's fine.
So you'll have to come back at some point.
All right, when I'm maybe more successful and stuff, we can look back at this conversation and try to give an update.
Yeah, that would be great. I really appreciate the time that you spent. I know you're super busy and all sorts, but it was great having you on. And yeah, any saved rounds?
Yeah, man. Hopefully I see you out there on the pitch here soon.
Yeah, we'll have to make it happen. We'll have to get your hip better, and then
get
out there.
Yeah, man.
All right. It was great having you, and we will see you guys next time. Peace.